So this is Workbench, and towards the left-hand side are all the different analysis systems. As you can see, there is Maxwell, there is all the structural mechanics, linear dynamics models that we can use from. So here, this goes to the whole workflow. Uh, I'm not going to go to the detailed modeling of the in the Maxwell, but as you can see, in Maxwell we can set up the entire electromagnetic analysis. We can define the coils, the permanent magnets. So this is the Maxwell interface. Uh, Within Maxwell 3D, there is a certain setting called Enable Harmonic Force uh, dialog, and this is where we can select on um, on what objects we would like to map. So it's all the tips. There are 6 tooth tips that we want to map on, and we can choose what is the uh, type of mapping that we would like to perform. Um, Also in the same interface, we have another dialog box called Advanced. This defines how we perform the DFT on this time data. So we perform a transient and then do perform DFT within Maxwell itself before we map it to the structures. Within the design, default design explorer is where we can define multiple parameters that we want to play with for optimization studies. And when we do that, these get carried over to the parameter set at workbench level, so we can use it for optimization studies. So these are, the different parameters, as you can see. We can also run it for multiple RPMs. So we can do it for 1 RPM, especially for making these waterfall plots. We have to run the simulations for multiple RPMs of the motor. So here is where we can also add RPMs on the Maxwell side, and in mechanical is where we'll also see how we can add more RPMs there. So once we do that, we can change the geometry from 2D to 3D, and then we can uh, you'll see how the geometry looks within Space Claim. So this is Space Claim, the CAD tool that the ANSYS CAD tool. It's a direct modeling tool that we can use to further improve the geometry. So this is the air box around that I'm hiding, and then this is the motor, the stator part with the teeth. So I'm going to skip this part because it just shows the cross section of the whole assembly. Um, Now what we do next is go to modal analysis, drag and drop modal analysis on the geometry and open up the modal analysis. Here is where we can define the boundary conditions and solve the modal analysis. So within modal analysis, you can mm, so this is you can basically simply define the correct units that you want to work with. Uh, you can define the modes that you are interested in, uh, and these are all the different parts. We are going to suppress basically the air components because they are of no interest for the modal analysis. Um, and we can solve. So we are not defining any fixtures. It's going to mesh, and it's also going to solve for the modes at once when we solve it. You can see the first 6 modes are almost zeros. Basically, of course, it's not constrained, so it'll have some rigid body modes in the beginning. You can solve for some of the modes here or all of them if you want. So I'm just plotting the deformation for some of the modes here. So the next step is performing the harmonic response analysis. As you saw we drag and drop at the solution level to perform a mode superposition harmonic response analysis. Um, Yeah, so this is the harmonic response environment. What we're doing here is the first step is create a name selection for all the tips of the teeth. So that can be done very quickly using the name selection feature. It selects using logic. So based on the same size, it selected multiple. Some of them it left. So we are going to add one more tip to name selection to capture those. And then together I'm going to merge them into one name selection. So name selection is just a way to group entities together so that you can use them in the downstream analysis. Um, so once we do that, we can then define the coordinate system. So we are going to define the cylindrical coordinate system, uh, which will be using the Workbench automatically creates all of these different contacts that you can see based on the assembly, uh, and it defines them as bonded contacts. You can look at the mesh as well here. So in this analysis, what we'll do is we are going to be fixing the outer surface, assuming that that is fixed, and use the modes from this modal analysis for the harmonic response. So we are just selecting all the outer surfaces to perform the fixture and do the modal analysis. When we do the harmonic response, we can so this is all modal analysis. So these are all the mode shapes. So we are looking at almost 2,500 modes here. You can look at the solution status. You can look at the participation factor summary in this dialog. So these are all very important because that define how many modes you want to capture for modal analysis if you want to perform any downstream uh, harmonic response, modal superposition harmonic response analysis. So you want to make sure the participation factor is high enough. After that, what we'll do is we will perform a harmonic response analysis. But before we do that, we need to drag and drop the solution onto setup, and that is what carries the forces and maps it onto the structure. So we are going to update the model, and once we update the model, we'll be able to see uh, the imported remote load folder. So that is what happens when you link the solution to setup, so Maxwell solution to harmonic response setup at the workbench level, and refresh the page. So you can see we are importing the loads onto tip all. That's the reason we created the name selection in the first place. And we are using the object-based mapping, so it's going to it's going to treat each of these faces or as one object, and then it's going to map the forces and moments onto each of these faces. And these are all the different the map that you can see, the forces and moments.
Krishna, sorry to interrupt. We're running close to the end of time today. So
Sure.
I'd like to be able to address a few questions if you'd like
Absolutely.
to maybe tie things up over the next minute or so.
Sure, I'll do that. Yeah, so this is
Thank
pretty
you.
much, yeah, yeah. So here is where we can change the number of RPMs, how many RPMs we would like to use, and then it'll have multiple imported remote loads folder for different RPMs. And using all of this, you can basically generate, waterfall plots because it needs multiple RPM data to be able to generate these. Um, so that's pretty much the overall workflow, as you can see. You can then take this to acoustic response analysis as well, and map the velocities to perform the acoustic analysis and integrate everything at the workbench level to do optimization studies. So this is the overall workflow for NVH, and so